So good morning guys. So we are starting with the first lecture of linear algebra, and in this lecture we will be doing the basics of linear algebra about like why is a linear function called a linear function and stuff. So let's start with the first topic, that is the linear functions. So basically we need to understand first that what does exactly does linear mean. So does linear mean, and by linear we always call, we know the two very clear principles, the principle of additivity, so additivity, and the principle of homogeneity. So these are the two principles of linear algebra and the linear functions, to be precise. And the superposition principle is often the main principle which is known to be the principle of linear functions to distinguish a linear function from a non-linear function. So what exactly is superposition principle? So superposition principle actually is the heart of linearity, and any linear function which is actually linear will actually support the properties of superposition. So mathematically, superposition means that we are having a function that is, suppose, t of x1, and we are having another function t of x2. So basically if a function we have is t, and then if we have a scalar alpha, which is a scalar, and I do sometimes make mistake while writing, so scalar, and we have a beta which is also a scalar. So what we can tell is that t of alpha x1 plus beta x2 will be same as alpha into t of x1 plus beta into t of x2. So this is the actual meaning of linearity in functions. So we would actually break down this theorem. So this actually comes from the two theorems which actually we told already before. So one is the additivity and another is the homogeneity, and we combine them together to form the superposition principle, right? So the additivity function is t of x1 plus x2 equals to t of x1 plus t of x2. This is known to be the additivity function. So you take any linear function, and if you see the linear functions have an additive nature, that is, suppose we take a linear function y equals to 5x plus 7. So if this is a linear function, so the things that is actually y equals to 5x plus 7, is it a linear function? First we have to check that. So a linear function, for that matter, has got a very important property, and we can confirm it from this example. So let's take two x1 and x2 values. So x1 and x2, let's take x1 as 3 and x2 as, suppose, 2. So t of x1 plus x2 means 3 plus 2 is 5. It equals to t of 3 plus t of 2. But are we getting it? So basically t of 5 is going to be 5 into 5 is 25 plus 7 is 32. So 32, and here t of 3 is 15 plus 7 is 22, and here 10 plus 7 is 17. So 17 plus 22 is 39. So this is not equals to this, which means, but this is a line, and line are always, we know lines are linear, but then we are not getting 32 and 39, not getting the additivity nature. So we have to understand this one thing, that any function, to satisfy the property or to satisfy, to have the definition, to call itself linear, it has to pass through the origin. So this is what is the actual meaning of linear function. Linear functions are never meant to be like this or like this. Even if the function is a straight line, it may not be linear. The only linear functions are always meant to move through origin. And if they move apart from the origin, then what we do is we first actually shift the origin, we make it come to the 0, 0 point, and then we perform all the operations needed for the linearization and other things we do on linear functions. So this is not a linear function. But suppose if we take y equals to 5x, now if we take x1 equals to 5 and x2 equals to suppose 3, so t of x1 plus x2 equals to t of x1 plus t of x2, which is actually t of x1 plus x2 becomes t of 8 equals to t of 5 plus t of 3, and if you check it, you will find that t of 8 is 40 equals to t of 5 is 25 and t of 3 is 15, and that becomes 40 equals to 40. So this is a linear function. On the contrary, we have another property for linear function which is called the homogeneity. So homogeneity tells us what, that t of c into t, or c for that matter, we can write t of c into x equals to c into t of x. So where c is a scalar, and we can also take a simple example again. So, or we can actually skip the example, because if we was taking y equals to 5x, and then we can just tell t into 3 into 5, 3 into x equals to 3 into t of x. So that is t of 3x is, and let x equals to, let's say we can take it as 3. So 3 into 3 is 9. So t of 9 is how much? 5 into 9 is 45, and we have 3 into t of 5, t of 3 actually. So 3 into 3 of 3 is how much? So 3 into 5 is 15, 15 into 3 is 45. So we find both of them are equal. So this also satisfied the conditions for homogeneity. So what we can tell actually by the superposition principle, the superposition principle is actually combining these two properties together, and we are getting that t of x1 plus x2, this is first property of additivity, and we have another t of c x1 equals to c into t of x1, and here also I forgot to write the full thing, that is t of x1 plus t of x2. So we actually combine these two properties together and we find the superposition principle. And the superposition principle, after all combining them together, we get that. So basically if we take t of suppose alpha x1, so this should be alpha into t of x1. Similarly, if we take t of beta x2, this should be equals to beta into t of x2. Now after that, if we actually combine them together, so this would become t of alpha x1 and plus t of beta x2, this should be equals to t of alpha x1 plus beta x2 according to the additive principle, and this equals to, we found out, alpha into t of x1 plus beta into t of x2. So the superposition principle is proved as t of alpha x1 plus beta x2 equals to alpha into t of x1 plus beta into t of x2. That's all for this video. We will again meet in the next video for the definition of field set and vector spaces. Thank you.